there will be an oblique shock that is formed, right? Which means that in region 2, you will have a the static pressure in region 2 will be higher than static pressure in region 1. Reason, region 2 is after an oblique shock. Okay. Now let's go to the so that's about the leading edge. Now let's go to the mid span region. Okay, the one that I have encircled. There also the flow is encountering a change of direction. Initially, the flow encountered a change of direction. As a result, we had an oblique shock. Now, what will happen looking at the geometry there when the flow encounters the change of direction there at the mid-span region? What is that? What is the physics there? Or what is the phenomena that is associated with the flow turning like that? What kind of a corner would that be? Do you consider it as a compression corner or an expansion corner?
Expansion.
Expansion, because the flow is turning away, or the flow is forced to turn away from itself. So you are going to have an expansion fan there. We will theoretically consider it similar to the Prandtl-Meyer expansion fan. Okay. Now the flow comes towards the end. Now at the end of it, the flow eventually has to be aligned with the mainstream direction. We are considering an orientation like this. So if the flow has to be oriented like that, now please remember that after the expansion, the flow becomes parallel to the new surface in region 3. Okay. Now after that, the mainstream has to be, so if it were continuing like this, it would go like this, whereas the mainstream direction is like this, which means that the flow has to be aligned. If the flow is to be aligned with the mainstream direction, it has to be turned back, which in turn means that the tail will lead to oblique shock. I hope it is clear to you. The flow after the expansion, if it follows the course, it won't be aligned with the mainstream. But physically, you need to have the flow going along the main direction, because you have a zero angle of attack here. And when that happens, when it has to be reoriented like that, it has to turn back towards itself, which means that at the trailing edge, you will have an oblique shock again. Okay, so now I request you to just look at the image and tell me at what point, 1, 2, 3, 4, you can see 4 regions, which will have the highest stagnation pressure. 1, 2, 3, 4. Which region will have the highest stagnation pressure? Anybody?
Sir, is it 2?
Yeah.
Is it 2, sir?
How do you think? Why?
Sir, after the shock, the pressure increases.
The pressure, static pressure increases. Stagnation pressure?
Oh, you asked stagnation. Okay, sir.
Yeah, I'm talking about stagnation pressure. Yeah. So I'm talking about what's the region, which region you will have the highest stagnation pressure?
Region 1.
Yeah, region 1, correct. Because what happens after that is an oblique shock. So there is going to be a stagnation pressure loss. So region 2 is going to be lower stagnation pressure. Now, how will the stagnation pressure in 2 and 3 compare? P02 and P03. What will be the comparison?
P02 is higher than P03.
That we think of it. P02 and P03.
So
P02 is higher than P03.
Sorry.
P02 is higher than P03.
Will that we think of it? Because what we have is an expansion fan. So what do we usually conceptualize when we do expansion, Prandtl-Meyer expansion? What do we say about stagnation pressure
Ah,
across?
It's equal, sir.
Huh?
It's equal.
It's equal, yeah, exactly. So P naught 2 and P naught 3 will be the same because stagnation pressure remains constant across a PM, an expansion fan. Okay, so P naught 2 and P naught 3 will be higher. And again, you have an oblique shock here again, which means that there is going to be a drop in stagnation pressure. So P naught 4 is going to be lower than P naught 3, etc. Anyway, so that's going to be the pressure. Now, if you look at the static pressure distribution, as we have seen already, you have a higher static pressure here because of the compression corner, and you have a lower static pressure here on this phase because of the expansion, and then it's going to be restored to the mainstream pressure. So as far as the body is concerned, you will have high pressure here, you have low pressure here, and when you have zero angle of attack, the same story is going to happen on the other side also. You will have a high pressure here, you will have a low pressure here, right, on the other side also, right? Okay, now with this physical picture in mind, now let's look at uh, how we are going to make use of the oblique shock and Prandtl-Meyer concepts to solve for the pressure field. So what I want you to carry forward from this slide is that we have considered a diamond difoil with zero angle of attack. Actually, the whole thing will be applicable when we consider at an angle also, but here we are considering zero angle. Now, and we see that the pressure distribution can be resolved by combining or by considering it to be a result of CD oblique shocks and expansion waves. Okay, now we are considering attached shock, which means that's why where we are, or rather we are considering a low angle, that is a sharp object, so we are fine with the attached shock theory. Now let's look at the consequences of this pressure distribution. In fluid mechanics, you would have heard of D'Alembert's paradox, right? D'Alembert's paradox, where D'Alembert's theorized that a body submerged in a fluid should not have a resultant force, etc., etc. You do you remember that, or you have come across that D'Alembert's paradox? Not sure. Okay. Anyway, D'Alembert's theory was that, or rather, it was sort of a surprising conclusion, which probably they could not explain at that point of time, and that was because they did not appreciate the role of viscosity. We are not going to details of D'Alembert's paradox, but then the theorization that when you have subsonic flow, I repeat it, when you have subsonic flow past a body, and if the flow is inviscid, then you will not have any drag, that is assuming there is no flow separation, etc. So if you have a body submerged in a inviscid fluid, you will not have a drag. I will reword the statement. If you have inviscid flow in subsonic Mach numbers, if you have inviscid flow around a body without having a vague flow separation, etc., you are not going to, the body is not going to have any drag. Why is it so? Because then in the absence of, say, a wake, etc., the drag is going to be fully, what kind of drag is that? Yeah, so in fluid mechanics, you have studied about pressure drag and friction drag and foam drag, right? Or friction drag and pressure drag, right? Friction drag, foam drag, friction drag and pressure drag. So when you have an inviscid board, when you have an inviscid fluid, which of this will be necessarily zero? You have an inviscid fluid, or when you have an inviscid fluid flowing past and submerged object. Which of the two types of drags that I mentioned would be necessarily zero?
Parasitic, sir.
Sorry. Huh?
Parasitic drug.
Yeah, the one that is related to the friction of it, the viscosity of the fluid, right?
Yes, sir.
That
Yes.
is when we, so the friction drag will be zero. Now, when friction drag is zero, it may, okay. So that applies to inviscid flow. So when I have when I have subsonic flow past an airfoil like the one that we have just seen, we will expect that there is no drag because there are no unbalanced forces. There is no resultant frictional forces because the flow is invisible, etc. But then this does not apply in supersonic flow. And it's quite easy to say, see why it does not apply in supersonic flow from what we have already discussed. When the in supersonic flow, even in the absence of viscosity, you have pressure differences, or you have force imbalance, or in other words, you may have a resultant force in a direction that is opposite to the flow, which is what we call as a drag, right? So this formation of drag, or this existence of drag, even in the absence of viscosity, in supersonic flow is because of the formation of the expansion waves and the oblique shocks. Now let's go to the top image here. I'll try to explain it once again here. You have a flow coming here. You have a flow, supersonic flow. You have oblique shocks. You have expansion fan, and because of that, you have higher static pressure on this surface. You have lower static pressure on this surface. Okay, now let's consider what happens on the upper half of the body, the upper half. Okay, we are considering zero angle of attack, just focusing on the upper half. There is going to be a pressure that is acting here, because of which there is going to be a resultant force, right? If the pressure is P, then P multiplied by this area will give you a resultant force which is acting like this. Now, there is another force which is acting here, a lower force actually. Right? Why lower? Because you have lower static pressure there. Why lower static pressure? Because of the expansion fan. So this pressure, so I have so I'll call it as P1. I'll call this as, rather, I'm sorry, I'll call the first one as P2. I'll go by the region numbering. I'll call this as P3. So I have P3 acting on this, I have P2 acting here, and I have P3 acting here. As a result of it, I have F2, the force, P2 into area. F2 acting here, I have F3 acting here. Now F3 is lower than F2 because P3 is lower than P2, which in turn means that there is going to be a resultant force. Okay, now this kind of force variations along the on the surface of the body is what leads to an imbalance force. And please keep in mind that when we said oblique shocks, and if you were to do oblique shock calculations, it's based on inviscid theory, and expansion fan is also based on inviscid theory. So we are not considering viscosity at all. Even in the absence of viscosity, because of the profile of the body and because of the shock waves and expansion waves created by the change in flow direction initiated by the shape of the body, you are going to have imbalanced force. And this and what I just mentioned about the top side, and the same story happens on the applies to the bottom side also. You will have a pressure here, you will have another pressure here. On the two sides, the pressures will be different, and there will be an imbalance. Okay, so so this resultant pressure is, or sorry, this resultant imbalance force is referred to as wave drag. Okay, that is, what we observe is that even in inviscid flow, you can have a resultant force, and that resultant force, which is purely because of the shock formation, is referred to as wave drag. Now, in this case, we can consider the term wave coming from because of it's happening from oblique shocks and expansion waves. Oblique shocks are actually shock waves. Expansion waves also are shock waves. Right? Oblique shock wave, expansion wave. Expansion wave. They're all waves, or the terminology is waves. So that's a reason in supersonic flow why we call it as wave drag. But I just want you to be aware that I'll come back to this term wave drag. I guess it comes from hydraulics, in fact, in the design of large ships, etc., and probably boats also. You have similar phenomena actually. That is the pressure differences on the body because of the waves actually. As I guess the terminology wave drag comes from hydraulics, hydrodynamics. Anyway, we are not concerned about it. There the physics is slightly different, but then we are coming back to what we are talking about here. Anyway, so in supersonic flow, even I'll before I even go to that simple derivation there, I'll pause here. I'll expect questions if you have anything to be clarified. From whatever we have discussed so far about wave drag and its formation and its cause. If you have any question, please raise. No. Okay, then we'll just see this formulation of it. This drag per unit span. Drag per unit span can be understood as the resultant pressure. Now, what is the resultant pressure? It's because of the force. It's because of, I'm sorry. Drag can be understood as the result of the resultant force. Now, where is that force coming? It's because of the pressure that is acting P2 and P3. P2 and P3. What is the force acting because of P2? That is P2 multiplied by, so P2 gives a force F2, which is equal to P2 multiplied by that length, right? Or rather, P2 multiplied by that projected area. That is, if you are talking about this phase, and we are talking about the area that is projected across the across the flow. So we can consider it as that included angle is marked as epsilon, the half angle. Okay, it's marked as epsilon here, a small angle, so that there is attached shock. So for this included angle, we can consider that projected area as P2, or rather projected area as L sin epsilon. L sin epsilon, right? We are just projecting it sin epsilon. So we'll get this dimension actually, right? So P2 into L sin epsilon is the force acting on this. Similarly, on the other side, it's P3 into L sin epsilon. P3 here, right? P3 into L. L is the length. We are considering a symmetric diamond diaphragm. So L, both are L. Both the sides have dimension L. Length is L. So P3 sin epsilon. So if you just simplify it, it can be written as P2 minus P3 into T by 2. T by 2 is nothing but the half length, half thickness of it. The whole the thickness is T, so T by 2 is half of it. So and you can see from the triangle that it's related to sine of epsilon, right? So L into sine of epsilon. So that can be written as T by 2. So if you just rewrite it, so it's 2 into P2 minus P3 into T by 2. 2 to cancel, you cancel here. So the drag can be written as P2 minus P3 into T. So the drag which results because of the pressure distribution P2 and P3 can be written as T. Now, where is this 2? I hope you follow the the derivation. Where is this 2 coming? Anybody? Why do you have a 2 there?
To include the bottom side forces.
Exactly, yes. So because I just considered the top portion, the same phenomena is happening on the other side also. So you need the twice that force. So that anyway, that 2 cancels with the t/2. So that we have a simple expression, d is equal to the resultant wave drag is equal to p2 minus p3 into t for a symmetric thin diamond shaped airfoil. Okay, in supersonic flow. So this drag force, which we write as P2 minus P3 into T, and this is what is known as wave drag. And this is quite unique about supersonic. I mean, high Mach number. Supersonic and hypersonic, but certainly above Mach 1, only because you have shocks and expansion waves happening only in supersonic range. So this is called wave drag, and I guess the importance of that should be quite obvious to you. In any supersonic application, aircraft wings or anything, you need to consider wave drag. And quite often, wave drag will by far exceed the friction drag and other forms of drag, pressure drag, etc. Pressure drag means this is actually a category of pressure drag. But friction drag, form drag, etc. So the importance of wave drag is very significant in supersonic flows, and it's even more in hypersonic flows, because as the Mach number increases, the resultant forces, pressures, difference in pressures, etc. is going to increase. So the same thing, the theory that we have applies to hypersonic flow, and it's even more important. The magnitudes of it are even more important in hypersonic flows. Okay. Now we'll see how how we estimate that on a flat plate. I just initially what we took here was a diamond-shaped diaphoil for which we formulated this, and we can the same thing can be applied to a flat plate at an angle of attack. You can calculate you just see the image here. We'll be working out the problem, but then I want you to be familiar with what we are talking about here. So you have a thin flat plate at an angle of attack. So you have an angle of attack of alpha, which is marked here. So this is alpha, in other words. Okay. So since it is at an angle of attack, on one side you have a compression corner because it's turning the flow in, whereas on the other side it's turning the flow away. So you have an expansion fan, right? This is because it's at an angle of attack, right? So you on one side, so it's not symmetric. Flow is not symmetric, unlike in the previous phase. So on one side you have an oblique shock, the other you have a fan. So which means that I can calculate P2 using P. So if I can calculate the pressure in this region using Prandtl-Meyer expansion. So if I know the upstream Mach number, and if I know the angle of deflection, which is the angle of attack here, basically alpha, then I can solve for this region and can calculate P3. Similarly, knowing the free stream Mach number and say this angle, I can calculate the shock region here. P3, this is P4, whatever. The pressure distribution on the side. Actually, this I guess this is P2 and this is P3. So P2 and P3 can be calculated using expansion fan and oblique shock respectively. So we are again using the shock expansion calculation. On one side shock, on the other side it's expansion. Because we are using the combination to get the entire pressure distribution. So once we know P2 and P3, then we can calculate whatever aerodynamic forces you want, lift, drag, etc., depending on the direction that you resolve it. vertically or horizontally. So the pressure distribution can directly leads to the calculation of the lift and drag. Okay, and it's a pretty useful method because the results that you get are quite close to computational results, and even many times close to experimental results as well. So despite the simplicity of the approach, the utility is quite good. I've taken this from somewhere where there is a comparison between, say you have a similar diamond shaped airfoil here, similar to the one that we have been talking about. Okay, and the flow with zero angle of attack. Simulations are done, and the calculations are also done using this model, shock expansion model, and they are compared. So you can see that it's quite close, 1.45, 1.44, etc. In different regions, the pressure distribution is given. So the Mach number, actually, these are Mach numbers, and these are static pressures. Static pressure, yeah, in atmospheres. Okay, so there you can see that they are quite close to more accurate computations, numerical computations, which means that the theory is capable of predicting the pressure distribution for simple shapes without large angles of attack and with a reasonable amount of accuracy. Okay, I think I'll stop here now. Any questions? By the way, we'll have at least one team presenting the assignment today, and then finish next in the next class. One team, I guess, we'll schedule today. Any questions before that? Okay. If not, we'll just spare 1 minute for this application of Newton's theory example, a numerical example. Quite straightforward, so I'm not going to explain it much. Calculate the L by D ratio, lift to drag ratio for a flat plate in Mach 18 with an angle of attack 10 degrees. So 10 degrees angle of attack, a flat plate kept in Mach 18. So quite high Mach number. So Newton's theory should be reasonably applicable. What is to be calculated here is the L by D ratio. We know the force, we have discussed it in the last 2 classes. So you know that force is rho v infinity squared s sine squared theta as per Newton's theory. And this is an attached shock case, so you don't have to worry about the least modification, etc. And we had derived yesterday a simple relation L by D equals cot theta. So that gives you, cot theta is given here. So you can calculate the ratio L by D as 5.67. Okay, so it's just a demonstration of how Newton's theory is made use of to calculate the aerodynamic force ratio, or rather lift to drag ratio. Okay, we'll stop here. I will request. By the way, I saw 3 teams have uploaded their assignments. Team 4 is yet to, I guess 2 and 5 2, 3 and 5 have uploaded. Team 4, anybody from team 4 right now? Team 4, please. Sun, Sanjay Krishna,
Yes, sir.
have you submitted the assignment or what?
Sir, yes, sir. I posted it in the file section.
Have?
Yes, sir.
So Okay, 2 and 3 have presented already, I think. Yeah, so then
Yes, sir.
you
Three has
yourself,
to
I mean,
present today.
huh?
Team
Huh?
3 has to present today.
Sorry, say that 3.
So, group 3 has to present today.
Okay, then you present it, please.
Yes, sir.
Group 3 can. All of you are there, Rajeshri,
Yes, sir. Sir,
who else?
is this-
Sangeeta and okay, all the 4 are there.
Yes, sir.
Yes, sir.
Okay. Yeah,
sir, is the slide
so you
visible?
can share and I can comment on your this one. So put that in. It's already on this one, right? Slideshow mode, right?
Yeah, is the slide visible?
Yeah,
Sir,
it is in slideshow.
yeah, yeah, it is visible, right?
Yes.
Yeah. Can I start now?
Yeah.
Good afternoon, everyone. Today, Group 3 will be presenting the results of the task that we were given. We had to plot the variation of density ratio with Mach number, the variation of density ratio with gamma for different values. Density ratio with Mach number for different gamma values, and we were going to compare the results between two relations. One is the Mach limit and the normal oblique shock relations. So the plot here shows how the Mach limit and the normal shock, the straight line corresponds to the Mach limit relation, while the other curve that's varying corresponds to the oblique shock, the normal shock relation. And in this plot, you can see the topmost two curves correspond to a gamma value of 1.1. These next two correspond to a gamma value of 1.2, and the bottommost correspond to a gamma value of 1.4. And through this graph, we can make some important observations. The first one being if you look at the graph and where the Mach limit converges better, as the gamma value increases, the convergence is also much more stronger at a lower Mach number. At say an arbitrary Mach number of 20, K for gamma equal to 1.2 and 1.4, the Mach limit converges with the normal shock relation for the static density ratio, while it does not do so for much lower values of gamma values, which is one major observation that we can make.
Just state that once again. What you said now. Please explain.
Okay. In this graph, if you observe, the Mach limit and the convergence of Mach limit and the normal with the normal shock relation happens at a much lower Mach number for higher values of gamma. So let's say take Mach number 20 for gamma values of 1.2 and 1.4. The convergence is much better, pretty accurate value compared to the gamma value of 1.1. The values do not really converge. Uh, the next is that the density ratio is higher for a given Mach number. Say Mach number of 10, the static density ratio is much higher for lower values of gamma and increases with as gamma value decreases. The next is, so what does this actually mean? That if the static density ratio is higher, in general, if we look at the shock tables, you can see that as the Mach number increases, the static density ratio increases. But here, if you see for a given Mach number of 10, there's a higher static density ratio for a lower gamma value, which means we can say that the effect of the shock is more pronounced for a lower value of gamma value, which is another observation that we can make. That's all for our side.
Okay, please go back to your observations. Correctly pointed out that we know the impact of shock being
So your voice is breaking. It's not very audible.
I see if it is better now.
Yeah,
Is
it's better now.
good. Okay. So you correctly mentioned that the impact of normal shock compression effect will be higher when
Yes.
you have a lower uh, lower value of omega, right? Can you think of any application for this observation?
Application of which observation, sir?
This basically when you say that, so basically what you're saying is that the density ratio is high when you have a lower value of gamma.
Yes, sir.
Right, density ratio across session, right?
Yes.
So can you think of any application where you can probably make use of this observation?
Um,
Not readily. That's okay. You can think of it. That's fine. Now, one more question is about the previous observation that you mentioned. This is actually very important. The previous one. Please go to that. This one. Yeah. So, can I ask anybody else in the group to comment? Sorry, I'll just open it. Three. Yeah. I guess Rajeshri has been talking, right? So maybe
yes, sir.
Renish or Ankita can or Sanjay can tell me. Say what she had pointed out was that when Mach number increases at higher Mach numbers, the convergence becomes slower. So what does it tell us about higher Mach number? Higher, I'm sorry. At lower values of gamma, the convergence becomes slower. What does it tell us? What does it tell us about the applicability of the hypersonic limit? So when we deal with gases of different gamma, what does this particular plot tell us regarding the applicability of the hypersonic limit? Anybody from the group can have other than Rajeshri can comment on that. Renish, can you please?
Sir, I can't say exactly, but for gases with low gamma value, like rare gases, this convergence is applicable only for greater Mach numbers, hypersonic.
Yeah, that is correct. So suppose that we are working with a 1 point, what is the highest value, lower value that you have, gamma equals 1.1.
1.1, sir.
1.1. Looking at the graph, where would you say it is okay or reasonable to start using the hypersonic limit application?
Above Mach number of 25, maybe, sir.
Yeah, maybe. Yeah, fine. Okay. This is a very important observation. I want everybody to note it actually. So, though we say density ratio tends to become 6, etc., it's only for 1.4. Gamma equals 1.4. And as we see here, it's a strong function of gamma. So, which means that, say, for example, for 1.1, 1.2 are not unusual. That's the reason why I want to emphasize this. They are not unusual in hypersonic flow applications, particularly when you have high temperatures and also when there are chemical reactions, which can be there. We have seen that in the effects of hypersonic flows, you can have chemical reactions, dissociation, etc., in which gamma value can be affected. Even if you are working with air, the gamma value of the region of interest can be different because of the chemical reactions. So in such cases, we should be very attentive to the actual value of gamma before we use any of the shock relations. That's what I want to highlight here, because gamma value has a strong impact on the shock and its consequences. Okay, I guess time is up already. We'll stop here. We'll continue in the next class. Thank you. Thanks to all of you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks.